Hope you're enjoying your break. So this is our review. A lot of what we covered in class on Thursday involves material. It's on the test, but there's some additional things that we need to talk about. So the first, integration by parts. So there were some, typical kinds of integrals that we dealt with where you had a product of two terms, one which was algebraic and one which was trigonometric, and we went through those. Those were fairly simple. And whether they're hard or simple, the basic procedure applies. So the procedure is you identify part of the product as a u and part of it as dv. And as you hopefully remember, the u is the one that you can differentiate. So the derivative is simpler than the original function. So in these particular two examples, x is the simpler function. Now the only case where, well, I shouldn't say the only case, but the most likely case where u is something other than x or x squared, x cubed, is if you have the natural log. Say if I have x times the natural log of x dx. In that case, the derivative of x is simpler than the function x, but the derivative of the natural logarithm, which is 1 over x, is also simpler. And so the other part of the question is, what is dv? And dv is a function which can be integrated using the tables. So, and really, usually it's the more complicated one. You want to take advantage of this fact. So this can be integrated. The integral of e to the x is e to the x. The integral of sine of x is sine of x. If you come down here, there is no integral for natural log in the tables. So that's why in this case, this is a special case where u is equal to the natural log of x, and dv would be equal to x dx. But in these other cases, u is x and dv is e to dx. Here, u is equal to x, dv is equal to the sine of x. So the one we did today was similar to this one, except we had this x squared. So typically if you have a product where x is to some other power than 1, then you have to use integration by parts more than one time. So these are the typical ones. There's the more complicated one, like e to the x sine x. That takes a lot of work. I'm not going to stick it out on a test. So we did that in class, and that was just kind of a special case. We also had the integral of the secant cubed, I think. We used integration by parts, and it was similar to this. But again, those are something that we're not going to do on a test. So you're either going to see some kind of simple product like this, or maybe where you have x squared or something like that, or x squared. You could put x squared here, and that still would be integrable. There are some other more weird cases that you can identify, but what I want you to do is to be able to go through this procedure where you identify u, identify dv, then what you do is you calculate du by taking the derivative of this and calculate v by integrating it. Again, in the example in class, we had the case where this argument was something other than just x, and it was reasonably simple to address. So you calculate, you choose these, you calculate those two. Then I want you to write this down on your paper. U dv, integral of u dv is equal to u times v minus the integral of dv du. So once you've done this, you can just plug those into the equation. And if it's a single integration by parts, then this second integral should be then something you can use the tables for, or use a simple u substitution. In the class problem, this was actually required integration by parts again. So you make the substitution. So then you substitute, after you write this down, you substitute u, v, and du into this equation. And then you integrate the integral of the v du, and then you're done. Again, you may have to use integration by parts on this the second time, which we did that in class today, so just make sure you understand it. Okay, so that's integration by parts. Usually involves products, but sometimes there are some special cases like the integral of the natural log of x dx, where it doesn't look like there's a product. There actually is. It's the product of these two things. Okay, the next thing was trig integration. We went through all kinds of different possibilities on that handout. But what I want you to be prepared to do here is either handle what we did in class, some kind of even power of the sign, where we use the pi-reducing formulas, or the other case is where we had something like this. So if I gave you sine cubed of 6x cosine squared of 6x dx. So when you have these products of sines and cosines, the thought process here is I'm going to either take a sine or a cosine and group that with dx. I'm basically doing u substitution. I'm just trying to figure out whether u is the sine or the cosine. And a lot of times it's actually better to figure out what du would be, and then you can go back and find out what u would be. If du is cosine, then u is sine, and du is sine. So we know, it's easy to figure out that relationship. So there are basically three cases. I'm going to present those three cases to you. One is where you have the sine odd, cosine even, and you have sine even, cosine odd. Then you have both of them odd. And then if you have both even, that's all the different ways you can do it. So let's say we have sine squared 6x cosine squared 6x dx. So how do you handle each one of these? Well, you always have to use, in these three cases, you have to use the Pythagorean identity at some point, which is sine squared. Now in this case, it would be sine squared 6x plus cosine squared 6x equals 1. So as long as the argument is the same, it doesn't have to be sine squared x. It can be anything, just as long as these are the same. So we're going to use this somehow or another. So for the case where you have an odd exponent of sine but an even exponent of cosine, you take one of the sines and you match that with the dx. And what that does is it leaves sine squared here, and then the second term doesn't change. So you get an even power, and you can only use the Pythagorean identity when you have an even power, so that's why you choose that. If I took one of these, I'd have both these would be odd exponents, and I couldn't use the Pythagorean identity. So my substitution in this case would be the sine of 6x would be u, and du would be equal to 6 times the cosine of 6x. So this would be du. This would be, actually that's the wrong way around. Okay. So that's the one thing. Du is actually involving the sine, so the cosine is u, and du is equal to 6, negative 6 sine of 6x. So what we have here is sine of 6x, so you'd have this substitution, you'd have du over negative 6. This one would be u squared, but this one's the problem because I don't have a substitution in terms of u. So this is where you would use the Pythagorean identity. Instead of sine squared 6x, you would use 1 minus cosine squared of 6x. So that's this. Then you multiply by the cosine squared of 6x and the sine of 6x times dx. So this bit here is negative du over 6. And then you get 1 minus u squared times u squared. And that's what you would integrate. So you'd integrate, we're basically using u substitution. You'd multiply this out, factor out the negative 1/6, integrate the polynomial here. Once you integrate it, then you substitute back in. So I'm not going to work every one of these out, but you can see for the second case, you take the cosine and put it over here. If cosine x dx is the derivative, then u has to be the sine. So then you would use the Pythagorean identity to rewrite the cosine in terms of the sine. So you have all this stuff in terms of the sine times the cosine. Now when you have both of them odd, you can do either one, doesn't matter. You can take the sine and put it here with dx, or you can take the cosine. Because it still leaves an even power with the one that you need to use the Pythagorean identity with. When they're even, this is where you have to use the power reducing formulas. We did this particular one in class. So you'd have to use the other power reducing formula for this one. 1 over 1 plus cosine of 2u over 2, you know, those particular ones. And then you just keep applying that until you were able to integrate it. Okay, so that's the kind of thing I'm looking for you to be able to do. Handle both, any one of these 4 cases, plus make sure you know how to handle the 6x or the whatever x. And again, that comes in through this du part. So typically you end up with just one, you know, either, in this case, either 6/6 or negative 1/6, depending upon which one of these you go through. You don't get it multiple times because it's cubed. And the only time that the constant inside the argument comes into play is when you're calculating du. Okay, and then you've got the other case, the tangent secant stuff. So what you have is something like this. You're going to have cases where you have secant squared. I'm just going to use x right now here. So you're going to have a du part here, and then you're going to have something else. And again, this is the derivative of the tangent. So it really doesn't matter what the exponent of the tangent is. I'll call that a to the x power. Now the secant has to be some even power. So this would have to be secant squared or secant to the 4th or something like that. Because if I had an odd exponent, I couldn't use the other Pythagorean identity, which says that the tangent squared of x plus 1 equals the secant squared of x. And again, it doesn't, if it's some other argument like 10x, tangent of square root of 10x plus 1 equals the secant square root of 10x. Okay, so that's whatever the argument is, you can use this result. So what you would originally have, say if you had tangent cubed of 3x and secant fourth of 3x dx. That's my original equation. You know, I have two choices. I can either grab secant squared to do this, or I could take one secant and one tangent. And I think actually in this case you could actually do both because of the fact this is odd. But let's not. So let's assume you don't know anything about this stuff up here. So I'm going to put my little screen up, and you're just given this problem. So the question would be, how should I rewrite this? Should I take a secant squared out here and then have tangent cubed 3x? Let me move this over a little bit. Should have tangent cubed 3x and secant squared 3x dx. That's one option, which would work because I would let u equal the tangent of 3x. Therefore, du would be equal to 3 secant squared 3x dx. So this would be u cubed, this would be du, and then I could rewrite the secant squared using the Pythagorean identity. Secant squared is equal to tangent squared 3x plus 1 times secant squared 3x dx. So then, using this u and du, I'd have u cubed times u squared plus 1 times du. And then I just integrate polynomials and then substitute back in here. So that would be one way of looking at it. The other option that I could do, if I given this problem, is I could take a tangent from each, a tangent and a secant. So I have, so if I do that, then I'd have secant 3x tangent 3x dx. So if this is du, then u would have to be equal to the secant of 3x. So du is equal to 3 secant 3x tangent 3x all times dx. So this part would be du. This part would be u cubed. I need to rewrite this in terms of the secant. So the trig identity that I would use would be tangent squared is equal to secant squared minus 1 . So that would be, this is my original equation. Again, what I've done is I've taken one tangent, moved it here, one of the secants, moved it there. So this is going to be du. So u has to be what the integral of that would be, which would be secant. So I said let u equal to secant. Derivative of the secant of 3x is 3 secant 3x tangent 3x dx. I have this is du, this is u cubed, this is not anything yet, but I use the trig identity. So finally what I have is u squared minus 1 times u cubed times du divided by 3. Because du is 3 times this, so secant 3x tangent 3x dx is du over 3. So there I have it. I have a polynomial, which I know I did great. So that's the kind of thing you want to do, is you just want to think about which one of these two options. Do I grab a secant squared? Do I grab a tangent, secant tangent? Is the resulting one left over such that I can use the Pythagorean identity on the appropriate thing? Okay, so that's kind of how it works with tangents. Then we have trig substitution. Remember, there are three cases you have where you have something square root of a squared minus u squared. You have the case of a squared plus u squared, or u squared plus a squared, doesn't matter. And you have the case of u squared minus a squared. So those are the, and you know, it can be this to the first power. So you could square this to get rid of the square root sign. So you're always looking for something that involves this kind of arrangement. Some constant squared minus some variable term squared. So in this case, your triangle looks like this. You might want to just draw these down, write these down. So in this case, u goes here, a goes there. The third side is going to be a squared minus u squared using the Pythagorean theorem. The substitution is the sine of theta equals u over a. And then you go through the whole thing, you calculate, figure out what x, you know, you'll solve for x. Take the derivative of x, get dx. You know, you can look at, we did a lot of examples in class. I'll give you little hints when it comes to the integration. When you have something squared plus something squared, just they're both positive, then the opposite side is a u, the adjacent side is a. That makes, from the Pythagorean theorem, the hypotenuse length is a squared plus u squared square root. In that case, you use the tangent of theta is u over a as your substitution. And then finally, if you have a variable part squared minus the constant part squared, you let u equal the hypotenuse and a be the adjacent, and therefore the, using the Pythagorean theorem, this is going to be u squared minus a squared. And the substitution we start with is secant theta equals u over a. So when you get to this problem, the first thing you're going to do is you're going to figure out which one of these three things to do. So you choose your substitution. Choose which substitutions I need to use. So that's step one. Then you're going to get x by solving for x in this. U is most of the time u is x, but if you have, like in the problem that we did today, we have 4x squared minus 9, the u in that case was 2x. But in all cases, you solve for x from this original substitution. Then you calculate dx by taking the derivative, whatever this is. So then you have the dx substitution. Then you take the square root term and divide by the constant term, and that's going to equal some trig function. For this, it involves the cosine. It's always the trig function that involves the ratio of the square root side to the constant side. Adjacent over hypotenuse is cosine. Hypotenuse over adjacent is secant. So you would use secant to get this part. Here, square root term of the constant term is opposite over adjacent, which is a tangent. So those are the functions that you would use. Here, this is the square root term that's in each one of these three cases, and the constant is the a. So then you can solve from that, you solve for the square root term, so it's just going to be equal to the constant times the trig function. Okay, So then you have these three substitutions. You plug those into your original equation. So, substitute x dx and the squared root term into integral. And what that's going to give you is you'll have an equation, an integral in terms of theta. Then you solve the integral. You simplify first. A lot of times you can cancel stuff out. Simplify before integrating. Then, after you simplify, you integrate. And most of the time it's some kind of trig integration. There are cases where you'd actually just integrate dx or d theta, which gives you theta. So when you integrate, your answer is going to be, in terms of your integral, is in terms of possibly theta, or in terms of the other trig functions, sine, cosine, tangent. And it's, probably not all of these, but there might be some of them. So your answer is going to be in terms of theta or any of the 6 trig functions. And then you substitute back to get the solution in terms of x. So we've got some of this. This might be your substitution, or the original, the sign, whatever these may be your substitutions, or this may be your substitution, or you may have to derive those. We give you that in class today. So that's integration, trigonometric substitution. So you just got to do them. The substitution part should be pretty straightforward, and the simplification should be straightforward. The integration, I'll give you a little bit of a hint, because I don't want you to mess the whole problem up because you can't solve the integral. I do want you to know how to do all the other steps. Those should be pretty easy. There's going to be 2 partial fraction problems. We did one in class today, which was the 2 distinct linear factors. So just know how to do what we did in class today. And make sure you know how to do a definite integral like we did in class today. So that was the one kind of partial fractions. The other kind of partial fraction problem, and I'll just go through the whole thing, is you're going to have something like 4x squared plus 3x plus 7 divided by a linear term. And I'm just going to give you a simple quadratic term, so it doesn't have a middle term. That makes it so you can solve the coefficients much more easily. So what you do is you do the partial fractions first, and then once you figure out the coefficients, then you can do the integrations. So I'm not going to include the integral sign here. I'm just doing the partial fractions. So when you have a linear term and a quadratic term, the linear term by itself has a coefficient, unknown coefficient of a in the numerator, and the quadratic term has a b and a c, bx plus c. So because there are 2 terms and they're different, you can just cross multiply them. So you'll get a times this denominator plus this denominator times bx plus c. And then you multiply out the right-hand side, so you'll get ax squared plus 6a for this part, and then you'll get bx squared plus, that's first, the inner is 2bx, the outer is cx, and the constant part is 2c. Okay, so that's your long equation. Then what you do is you break it up into the different parts. There's the constant part, there's the linear part, and the square part. So you go to the left-hand side and you see you've got 4 is the coefficient in front of x squared. We've got an a and a b, so we get a plus b equals 4. We look on the left-hand side, you've got 3 is equal to, we've got 2bx, so we do 2b plus c, that's 2bx plus cx, so it's 2b plus c. And then we have a constant of 7 on the left-hand side, and the terms that involve constants are 6a minus plus 2c. So those are 3 equations and 3 unknowns. Now, if you want to use your calculator to do an invert matrix, that's fine, but I'm going to show you how to do it if you don't know how to do that or you don't have the appropriate calculator. So what we're going to do is we're going to solve these and substitute into the third equation. So the third equation is terms of a and c. What we want to do is make this in terms of the other variable, which is b. So you solve the first equation for a, so that's 4 minus b. You solve the second equation for c. C is 3 minus 2b. So subtract 2b, get c, subtract b, I get a. So then you substitute those into the final equation. So you have 6 times a from the first equation is 4 minus b. Then you have 2 times c. C from the second equation is 3 minus 2b. And you see now it's just in terms of b. So you multiply everything out. 24 minus 6b plus 6 minus 4b. So we get 7 is equal to 30 minus 10b, or b equals negative 23 over negative 10, or 23 over 10. So that's b, if I did that correctly. So once you have b, then you go back and you can get the other stuff. So a is 4 minus b. B is 23 over 10. So that's 40 over 10 minus 23 over 10, which is 17 over 10. So that's a. Then you go to the second equation. C is 3 minus 2 times b. B is negative 23 over 10. So that's 3 is 30 over 10. Then we have negative times a negative is positive. 46 over 10. So that's 76 over 10, which you could simplify that down. 5 by 2, you get 38 over 5. So those are my coefficients. So a is 17 over 10. B is negative 23 over 10. And C is equal to 38 over 5. Let's put it over 10. Let's do it, stay it in 10, just because I think it's going to be easier. No, we can do it. We can leave it simplified. Now, the other way to do it would be to set it up in a matrix. So let's just check, make sure I did it right. So the matrix is going to be 1, 1, 0, because I've got 1A, 1B, 0A for here, 2 B's, and 1 C. And then finally I have 6 A's, 0 B's, and 2 C's. So that's my coefficient matrix. Then I have my unknown matrix. And then I have my vector matrix here, which is going to be 4, 3, and 7. So now I'm going to enter those into my calculator. Okay, so let me go. Somebody coming to my office. Anyway, it won't be any bigger than a 3 by 3. We did that one in class. It was a 4 by 4, but this will be 3 by 3. So I'm just entering my matrices right now. So hopefully you do the same thing. If you might want just to do this to check your result. And you have to be 100% sure you did it correctly. Chances of making the same mistake is pretty slim. So I take A, I take the inverse of A, and I multiply by B. And I get that, and then I change it to a fraction. Oh, anyway, let's see, change it to a fraction. So I'll do that math, fraction. So I get A is 17 over 10, B is negative 20. Oh, must have made a mistake. Let me just check my numbers here before I say that I made a mistake. I got the sign wrong on that. Because what I got was 23 tenths instead of negative 23 tenths. Oh, and I got that right. So it's 22. I don't know where I got negative. I guess I just read that wrong. So I did it right, except I got to finish this off and make sure that C is correct. Okay, so C is equal to 30 tenths minus, then B is positive 23 tenths. So then I have 66 tenths. So I get negative 36 tenths, which is, still not doing very well here with the math, am I? 2 times 26 is 46. 30 minus 46 is negative 16, so negative 16 tenths, which is negative 8/5. Okay, finally got that right. Negative 8/5. So those are my coefficients. So my final integral here is going to be, so you take your first coefficient, 17 tenths. That's going to be the integral of 1 over the linear factor, which is x plus 2 dx. And I take my next coefficient, which is 23 tenths, and that is going to be multiplied by x over the quadratic term, which is x squared plus 6 dx. And then the third term is negative 8/5, the integral of 1 over x squared plus 6 dx. So that, originally I had bx plus c over this whole thing, and I broke it up, so I just took the coefficients and took those out front. So the final answer is 17 tenths natural log of the absolute value of x plus 2. The second one is you need a 2 here to make this thing work out exactly. So this is u and this would be du. So you end up having to divide by 2. So when you divide by 2 here, I'll get 23 20ths, the natural log of the absolute value of x squared plus 6. Okay, so what I'm doing is basically I'm putting a 2 here, putting a 2 there, and this is du and this is u, so the integral of du over u is the natural log of u, and then you got that. And then finally, you've got 8/5, and the integral of this is the inverse tangent. So what you have is 1 over a times the arc tangent of u over a. And then you add your arbitrary constant c. So this is times. So this becomes an arctangent thing. And then we could just clean it up just a little bit. That last term, because we have the radical in the denominator. So if I multiply by the square root of 6, I'll get 8 square root of 6 over 5 times 6 times the arc tangent of x, the square root of 6 over 6 plus c. So if I multiply both the numerator and the denominator by the square root of 6, I get that. And the only thing is this could be simplified because you've got a common factor of 2. So you'd have 4 over 15, 4/15. 4/15 square root of 6 times that whole thing. Okay, so that's pretty much it. You're going to have an integration by parts problem. You're going to have a trig integration problem that involves sine and cosine. Just look at the exponents, decide what to do. You're going to have a trig integration problem that involves tangent and secant. So we looked at the two options. We've got the trig substitution problem. Here's the basic method. You've got partial fractions. You've got the one we did in class today, which was 2 distinct linear factors. And then you've got the other case where you have a distinct linear factor and a quadratic factor. And the ways of solving for the coefficients is different when you use this method. You have to solve. In this case, we use the substitution, or you can use the matrix to solve for the unknown coefficients. And once you have that, then you can rewrite the original integral in terms of those coefficients and the linear factors and the quadratic factors. And then the integrals are pretty simple after that. I'm not going to include anything about L'Hopital's rule or improper integrals on this test because there's enough stuff to do without that. Okay, and the last two items on this test will be L'Hopital's rule and remember what that does is it looks at the limit of a rational function. So it's the limit as x goes to c of f of x over g of x, and this is the case where initially when you plug in x equals c into the function, you end up with an indeterminate result. So it could be 0 over 0, it could be infinity over infinity, any one of the indeterminate forms. And what L'Hopital's rule says is that the original limit of the ratio of these two functions is equal to the limit to the same x value of the ratio of the derivatives of those functions. So there are two fairly simple problems on it there. One will involve a well, no, I can't say that. Okay, so there were a couple of things that we looked at. We looked at cases where we had the dividing out technique. So those are just polynomials that we took the ratio of, and those were indeterminate at the value of x, and we just took the derivative of the polynomials. So polynomials. You think a look at the first two problems on the handout. and then you had rational. Well, we had, and what we did here with polynomials is dividing out. That was the classical way of doing it, but you can also use L'Hopital's rule. And there was also the case where we had rationalization. So there was, that was the second problem on the handout. Rationalization, okay. And then there were these, which were the ratios of polynomials and exponentials, something like that. And in these cases, the limit either was infinity or it was 0. And you applied the L'Hopital's rule multiple times until you got to a point where the one that was the polynomial ended up just being a constant. So, when you take the derivative, the exponential function, in this case, you get 2 times the original function. So this one always goes to infinity. But if you take the derivative of the polynomial part enough times, in this case, if you take the subsequent derivatives, at some point you'll get to just a constant. So, in this case, I've taken the first, second, third, fourth derivatives. So by the time I've taken 4 derivatives, the numerator is 24. But the denominator is going to be, multiples of this. So when you take the first derivative, you get 2. When you take the second derivative, you'll get 2 times 2, which is 4. Third derivative, you'll get 2 times 2 times 2, which is 8, and then you get 16. So if I take the fourth derivative of e to the 2x, I'll get 16e to the 2x power. And at this point, both the numerator and the denominator are not infinity. The denominator becomes infinity, the one that's associated with the exponential term. And so we get 24 divided by infinity, which is 0. Now if we did it the other way around, if you had x to the e to the 2x in the numerator and x squared in the denominator, then you get this thing flipped around, and you'd have infinity in the numerator and a constant in the denominator. And so in that case, you get infinity. Okay, so those are problems like that. We also looked at problem, for example, where we had the sine of 2x over the sine of 3x or something like that. And again, if you plug 0 in here, you're going to get an indeterminate result. But if you apply L'Hopital's rule, you'll get the cosine, and you'll also get this factor of 2 here because of the derivative and the chain rule. You get a factor of 3. If you take the derivative here, and you'll end up with the derivatives will involve the cosine, and the cosine of 0 is 1, so you don't end up with the indeterminate result. So look at this as well to be prepared for the test. Okay, and then the final thing is improper integrals. Now I'm not going to give you the one that you have to use the L'Hopital's rule because that's a long problem. So it'll be ones that are fairly straightforward. Something like the integral from 1 to infinity. 1 or any number. It could be any number besides 1. It could be 2 to infinity of, say, 1 over x cubed, or the integral from 1 to infinity of 1 over the square root of x. And the key thing here is they're not that difficult of integrations as long as we rewrite this as x to the minus 3 power, and this would be x to the minus 1/2 power. So, the integrals are not that difficult. The big thing here is I want you to use the proper notation. So you'd have the limit as x goes to infinity, as b goes to infinity, of the integral from 2 to b. Likewise, the same thing over here. This would become the integral from 1 to b of the limit as b goes to infinity. So something along those lines. We did quite a few of those in class. Some of them converge and some don't converge. And then you had the case of the integral from 0 to 1 of similar kinds of functions, 1 over x cubed, or the integral from 0 to 1 of 1 over, say, the cube root of x dx. What happens here is that the function goes to infinity at x equals 0. So again, what we would do is we would, in both of these cases, we would write them as such where the limit where the function goes to infinity is replaced by b. And we'd also rewrite this as x to the minus 3 power before we integrated it, before we tried to integrate it. And in this second case, we'd do the integral from b to 1 of x to the minus 1/3 power, because the cube root is to the third power, the 1/3 power, and when you move it to the numerator, it becomes negative. And they're always going to be these kinds of functions because they're always going to have negative exponents, because the only time an improper integral has a chance of converging is when the function decreases like this. And whether it converges or diverges depends upon how quickly it approaches the x-axis. So, be able to take any one of these four similar, it's not going to be exactly this, but they're going to be kind of like this. But make sure you make the substitution using this limit thing and know how to, do this in-depth. This is a definite integral, but where one of the limits of integration is a variable instead of it's a number. So what you end up with out of this is an equation as a function of b, and then you take the limit as b goes to 0 in this case, and b goes to infinity. And either when b goes to infinity, either the b term is going to go to 0 or it's going to go to infinity. If it goes to 0, then that means that term drops out, and you probably you'll have a finite result. If you plug b in and the function goes to infinity, the b function goes to infinity when b goes to infinity, then it diverges. So like I said, you don't have to worry about the one that we looked at in class that was more complicated. Just one of these simple ratios of 1 or some constant divided by x to some power, and it may be an integer power, or it may be a fractional power. And some of these converge and some of these don't converge, but I'm going to hopefully remind you to think back on that. I'm not going to tell you the answer. Okay, so that's it for this test.